dear students. Today I will give you some details on the problems related to transmission lines. So again, I am a course instructor on Samba, and our course name is Mechanical Engineering. In this course, there will be four type of problem topics that we will discuss. First type is reflection coefficient and transmission coefficient. Second type is standing wave ratio. Third is line impedance, and fourth is Smith chart related problems. So I will discuss four these kind of related problem topics. First of all, according to the theory that we have known previously, what is the reflection coefficient? Reflection coefficient is a coefficient of the ratio between reflected wave divided by transmitted wave that we have known previously in the lectures. There is a mathematics that you can see here. A certain transmission line has characteristic impedance of 75 plus J 0.001 ohms. That is the characteristic impedance. That means that is the value of Z0. That is the value of Z0. I have to note it. That's the value of Z0. And another, and it's terminated in the load impedance. That means 70 plus J50 ohm. That is known as the ZL. So first of all, we have to compute the reflection coefficient. The reflection coefficient, the equation of the reflection coefficient is ZL minus Z0 divided by ZL plus Z0. So after calculating it, we can get the reflection coefficient. After that, the transmission coefficient, we have to find out transmission coefficient. So the transmission coefficient, the equation is 2ZL divided by ZL plus Z0. So again, we will put the value and we will get the answer clearly. And third part is that we have to calculate the relationship that is shown on. That means it is from the book, but the relationship is the T square ZL divided by Z0 1 minus gamma square. Here gamma is the reflection coefficient, you know. So we have to prove it. So here first of all we have to find out in the left hand side, that is T square, and we find out the value. After squaring it, we will get this, and then ZL by Z0 1 minus gamma square. We have to just calculate it, put the value, and we will get the value from here. So here two values are quite same. So thus the equation is verified. And the number is the fourth number, the B number. The transmission coefficient equals the algebraic sum of 1 plus the reflection coefficient. That means we have to prove that transmission coefficient T is equal to 1 plus gamma. So if we put transmission coefficient, we get this, you know, and if we put 1 here with the gamma, we get T. So that can be verified also. So in this math, we have find out four things according to the equations and other laws of reflection coefficient and transmission coefficient. In the second part, we will got to know that a transmission line has characteristic impedance of Z, as you know, Z0, and is terminated in a load impedance, that is ZL. So you have to calculate the reflection coefficient and the standing wave ratio. That is the equation of reflection coefficient. We have studied earlier. Just calculate it and you will get it. And that is the standing wave ratio, equation of standing wave ratio. That is standing wave ratio is noted as a rho. Rho is equal to 1 plus gamma divided by 1 minus gamma. Just put the value and get the ratio. That is the standing wave ratio. I have told you before what is the standing wave ratio. Standing wave ratio means if it is a wave that propagates through there. So if there is a backward wave that is a similar like that, so that is known as a standing wave, that creates a standing wave. So this kind of ratio are known as a standing wave ratio. And that is the standing wave ratio. The third type of method is the line impedance, to calculate the line impedance. Here you can see that a lossless line has a characteristic impedance 50. That means that is Z0. Characteristic impedance is Z0, and is terminated in a load resistance 75. Z is 75 and Z0 is 50 ohms. That is 50 ohms, and that is 75 ohms. So the line is energized by a generator which has an output impedance of 50 ohms. The output impedance is Z output is 50 ohms, and open circuit output voltage is 30 volt. The line is assumed to be 2.25 wavelength. That means we know the value of lambda, 2.25 wavelength long. So we have to determine first of all the input impedance, that is a Z input, and then we have to find out the magnitude of the instantaneous load voltage, ZL, and last of all we have to find out the instantaneous power delivered to the load. Now coming back to the point that how you could calculate the factor. So first of all, there is we have to find out input impedance, that means Zin. So a Zin, particularly it is one kind of Z naught square divided by ZL. As we can see here just resistance is there, so we can write it out R naught square divided by RL. It's like this. So 50 square divided by 75, we will easily get the input impedance. But how we can get? First of all, there are some wavelength issue. The wavelength is lambda is equal to here 2.25, that is 2.25 long, and the main thing is that this wavelength should have to complete it with a quarter wave line. Okay, what is quarter wave line? If it is a sinusoidal waveform, the total wavelength is just like that, from here and there. Okay, that is the lambda. Okay, and if you want to find out the half of the wavelength, we will get lambda by 2. That means it could be a positive half cycle or a negative half cycle. But if you take the lambda by 4, that means you are taking the maximum point of voltage or maximum point of amplitude, whatever it might be. It might be an electrical field, it might be a magnetic field, whatever it might be. But lambda by 4 is gradually the thing that when the thing is on maximum. Okay, so that is the condition. In which condition we will do it? First of all, 2.2 wavelengths looks like a quarter wavelength. How that can we understand that is a quarter wave line? First of all, beta d, in previous equations there are some equations in wave equations. The beta means the phase delay, and d means the distance. Okay, the distance between the transmission line from the load, from the source to load, the distance between the line, that is d. So twice pi by lambda, as we know beta is twice pi by lambda divided by dash by lambda, and lambda by 4. So after that we will get pi by 2. Okay, so how that can we understand that is lambda by 4? Because there is 0.25 here. If 2 is in integer number, so 0.25, that means that it will be lambda by 4 here. In certain condition it will be a lambda by 4 here. So you will get the phase delay beta d is equal to pi by 2 after calculating it by this condition. So that is an important part to understand the mathematics in to calculate the later parts. Okay, so from here there is no relationship between this, but from B, when you calculate the reflection coefficient, that means RL minus, that's ZL minus Z0, you can write it down, ZL plus Z0. So as it is resistance, so RL minus R0 or RL plus divided by RL plus R0 is there.